This video is a calculus lecture on related rates problems. So in general, we're going to talk about what a related rates problem is. So it's an application problem where you're given information about several different quantities and the rates at which those quantities are changing. And what you're being asked to do is to find what we call the missing rate. So there's going to be one quantity and the rate at which that quantity is changing is unknown. And you got to use the information in the problem to figure out the rate at which that quantity is changing. So to illustrate how we approach this type of problem, I'm going to do an example. So in this case, we've got an oil spill. It's spreading in a circular shape, and the radius of the spill is increasing at a rate of 20 feet per hour. And what we want to know is the rate at which the area of the spill is changing when the radius is 150 feet. So this is a really classic type of related rates problem. So the way that you want to think about this is that we've got two quantities. We've got A, which is area, and R, which is the radius. And area is changing with respect to time. So we can think of dA dt as being what we want, right? So they're saying at what rate is the area of the spill changing? So dA dt is what they're asking for, the rate at which area is changing with respect to time. But they tell us that dr dt is the radius of the spill is increasing at a rate of 20 feet per hour. So in this case, we're looking for dA dt, they give us dr dt. So we want to know, how do we use the fact that we know what the rate at which the radius is changing to find the rate at which the area is changing. And the relationship between area and radius is the equation A equals pi r squared. That's the formula for the area of a circle. And so that's how the actual area and the radius are connected. So how are these rates of change connected? So what we're going to do is we're going to take the derivative of both sides. But we're not going to take the derivative in the normal way. We're going to think of area as being like A of t. And we're going to think of R as being like R of t, because both of these things are changing with respect to time. So we're going to take the derivative of both sides, but we're going to take the derivative with respect to t. So it's going to be implicit differentiation. On the left-hand side, the derivative of A is dA dt, or you could think of that as A prime of t. And then on the right-hand side, pi is a constant multiple. And to take the derivative of r squared, we're going to need the chain rule. So if we think of r squared, the way we want to think of that is instead of r squared, we want to think of that as r of t all squared. Remember, we're thinking of r as being a function that's changing with respect to time. So the chain rule would tell us the derivative of r squared is 2r to the first power. But then by the chain rule, we're going to multiply by the derivative of r, which is dr dt. Okay, so now this is our relationship between the rates. So when we talk about this being a related rates problem, this equation that we've just written down with the dA dt and the dr dt is a relationship between the rates of these quantities. So now we have to plug in what we know. We're told that dr dt is 20 feet per hour, so we're going to put 20 feet per hour in for the dr dt. dA dt, that's what we're looking for. That's what they want to know. So we're not supposed to be able to plug in for that because that's an unknown. And then they also tell us when the radius is 150 feet. So at this instant, the radius is 150 feet. And so if we plug all that in, what we get is dA dt equals pi times 2 times 150 feet times 20 feet per hour. And when we work all that out, we're going to get 6,000 pi square feet per hour. So that would be our final answer. Sometimes we'll need an approximate answer, in which case we would just take that 6,000 pi and plug it into our calculator to get a decimal. But in this case, our exact answer is going to be 6,000 pi square feet per hour. So here's the basic outline, and you might want to take a look at this and jot this down in your notes for the outline for solving related rates problems. It's really a step-by-step process. These are all going to be word problems, so they're really all going to be a little bit different. You're never really going to see the exact same problem twice. So you want to read the problem carefully and draw a picture if you need to. We could have drawn a picture of a circle in the previous problem. We want to identify the given rates and the unknown rate. We did that. We knew that we were looking for dA dt, but they gave us dr dt. Then we want to write an equation that relates the quantities in the problem. In the previous problem, that equation was the formula for the area of a circle, so that's where our equation came from. And then we took the derivative of both sides. We were careful to take the derivative with respect to t, using the chain rule when necessary, whenever we use implicit differentiation. And then we substituted the known information and solved for the missing rate. And then finally, the answer seemed reasonable because we were looking for the rate at which the area was changing, and we ended up with square feet per hour. That makes sense in terms of a rate of change of area. And we didn't get, like a weird negative number or something like that. We didn't get a number that didn't make sense in terms of the context of the problem. So let's walk through those same kinds of steps again, and let's do another different kind of example. So this time we've got sand falling from an overhead bin and accumulating in a cone-shaped pile that has a radius that's always 3 times the height. So I'm going to draw a picture here to help me visualize what's going on. So we've got this cone, and the sand is falling and making this cone bigger. That's the idea. So the sand is falling at a rate of 100 cubic centimeters per minute. At what rate is the height of the sand pile changing when the radius is 150 centimeters? And then we're going to use the formula this time. Instead of having to know the formula for the area of a circle, as we did in the first example, here I'm giving you the formula for the volume of a cone. It happens to be 1/3 pi r squared h. Okay, so what are we being told here? All right, so let's try to identify all the information here. So we've got the radius that's always 3 times its height. That seems like that's going to be important. So that's telling us that r equals 3h. We're also told that the sand is falling at a rate of 100 cubic centimeters per minute. Now, they don't specifically tell us that this is a rate of change of volume, but that's what it is, right? So the volume of this pile is increasing at a rate of 100 cubic centimeters per minute. So in other words, dV dt is 100 cubic centimeters, so centimeters cubed, per minute. And then let's see what we also know. At what rate is the height of the sand pile changing? So this is them asking the question. So dH dt is equal to question mark. And then it says when the radius is 150 centimeters. So that's when r equals 150 cm. Okay, so that's how I sort of pick apart the information in the problem and write it as either a rate or an unknown rate or a relationship between the variables. Now I'm ready to start thinking about taking a derivative. So we've got v equals 1/3 pi r squared h. But if we were immediately going to take a derivative here, we're going to run into a little bit of a problem. Because on the right-hand side, both of the radius and the height are changing. And so if I was going to take my derivative with implicit differentiation on the right-hand side, I'm going to need to use the product rule, because r squared is a function, h is a function, and that looks like that's going to be a bit of a mess. So before I take the derivative, I'm going to use this fact that they gave me, that r equals 3h. I'm going to simplify my formula before I take the derivative. So instead of r there, I've got 3h. So I've got 3h squared. And then when I multiply that out, 3 squared is 9. 9 times a third is 3. So I get 3 pi. H squared times h, that's going to be h cubed. So just doing a little bit of algebra there. Now I'm going to take the derivative of both sides. So now on the left-hand side, I've got dv dt. On the right-hand side, 3 pi is a constant multiple. The derivative of h cubed is 3h squared times dh dt. And that extra dh dt, again, comes from the chain rule. And now I can plug in the information that I'm given. Okay, so dv dt, they told me that that was 100. So I'm going to put 100 here, 100 cubic centimeters per minute. 3 pi, I know what that is, that's a constant. dH dt, that's what I'm looking for. So I'm not supposed to be able to plug in for dH dt here because that's going to be the thing that I want to solve for. But now what's h? They didn't tell me that. They told me that r was 150, but they didn't tell me what to plug in for h. So now's where I've got to use this relationship one more time. I know that r is 3h, so 150 is equal to 3h, so h equals 50. And so that's what I'm going to put in here for my h. So if I solve this, I have 100 equals, 3 pi times 3 times 50 squared. 3 pi times 3 times 50 squared, and then dh dt is what I want to solve for. So that's going to be 100. 100, my pen's freaking out here. Come on. So 100 divided by, that's going to work out to be 22,500 pi. That's going to be my dH dt. And the units there are going to be centimeters per minute. Again, that's my exact answer. I could simplify that. I could put that on my calculator and get a decimal answer, but that's what that works out to be. So again, follow the steps of this process. If you need to rewind the video, watch this example again. Again, how did I read the problem? How did I pick out what the information was? How did I set up my equation? How did I take my derivative, right? All of those steps should be steps that you should be able to follow and do on your own when you start doing these problems for yourself. Okay, let's do one more example. So this time we've got two airplanes converging on an airport. One travels due west towards the airport at 100 miles per hour, and the other travels due north towards the airport at 160 miles per hour. Assuming the planes maintain constant elevation, how fast is the distance between the planes changing when the westbound plane is 200 miles from the airport and the northbound plane is 480 miles from the airport? Okay, so one of the planes, so if this is the airport, one of the planes is traveling west towards the airport. So west is over here. Move my name of my airport. So west, if we're thinking about normal directions on a map, west is traveling to the left. So that would be going in the west direction. So that's where my first plane is. Maybe we'll call this plane number 1. And then the other plane is traveling north towards the airport. So again, using normal map directions, north would be up. So maybe we'll call this plane number 2. And then the question is, how is the distance between those planes changing? So typically in these kinds of problems, when we have a distance variable, we usually call it s rather than d, because d is a variable that we're going to use for derivatives, and so we don't want to get ourselves confused. So I usually use s for distance here. And then we've also got these other distances. So we've got plane number 1, which maybe I'll call that p for plane, and then plane number 2 distance, I already used p, so maybe I'll use q just because it's the next letter in the alphabet. So I've got my distances labeled here. So now when they tell me that one plane travels due west towards the airport at 100 miles per hour, remember that velocity is the rate of change of position. And so if plane number 1 is p miles away from the airport, one way to interpret what we're saying here when we say that the plane is traveling at 100 miles per hour is about the derivative dp dt. Now, because the plane is traveling towards the airport, that distance is going down, right? The plane is getting closer to the airport. And so that derivative would be negative 100 miles per hour. Similarly, the other plane travels due north towards the airport at 160 miles per hour. So that's telling me dq dt is negative 160 miles per hour. Now, the planes maintaining constant elevation, that's just so that you don't have to worry about thinking about this problem in 3 dimensions, right? So the planes are at the same altitude and we don't have to worry about that. So now what we want to know is the rate at which the distance between the planes is changing when the westbound plane is 200 miles from the airport and the northbound plane is 480 miles from the airport. So in other words, we want to know what's ds dt, so ds dt equals question mark, when p, that's the westbound plane, so that's 200 miles, and q, that's the northbound plane, is 480 miles. Okay, so we've got all this information, right? So all of this, right? How fast is the distance between the plane changing? All of that was that last thing that I wrote in blue down there. Okay, so what we're missing here is the relationship between these variables. So in the first problem that we did, it was a circle, and we were talking about radius and area, and we know that the relationship between radius and area is pi r squared. In the second problem, we were talking about volume and height and radius, and in that problem, I gave you the formula. Here, we've got these 3 distances, and nobody gives us a formula, so we have to sort of figure out what's the relationship here between P, Q, and S. Well, what you hopefully notice is that those 3 distances are 3 sides of a right triangle. And so in fact, what we have is the Pythagorean theorem. We have a squared plus b squared equals c squared, or in this case, p squared plus q squared equals s squared. And so that's going to be the relationship that I have between my variables p, q, and s. And so my relationship between my rates, I'm going to get by taking the derivative of both sides. Now again, remember, in these related rates problems, we're taking the derivative implicitly with respect to t. So the derivative of p squared is not just 2p. It's 2p times the derivative of p by the chain rule, that's dp dt. Similarly, the derivative of q squared, that's 2q dq dt, And the derivative of s squared, that's 2s ds dt. And again, if you're wondering where are those dp dt, dq dt, ds dt, where are those coming from? They're coming from the chain rule. So remember, the chain rule says you take the derivative of the outside function, and then you multiply by the derivative of the inside function. Okay, so now we're going to plug in all the stuff that we know. So we know that dp dt, we know that's negative 100. We know dq dt, we know that that's negative 160. ds dt, that's what we're looking for, so we're not supposed to be able to plug in for that. That's the thing we want to solve for eventually. We're also told that p is 200. We're told that q is 480. But we also don't know what s is. We've got two things that we don't know, right? Everything on the left-hand side is all numbers. We've got stuff to plug in there, but we don't have anything to plug in for our s. So what we can do is we can go back to the original equation. Remember, we're looking at the point in time where p is 200 and q is 480. So we can plug those in. P is 200, q is 480, and we can use that to solve for s. Now, we wouldn't have wanted to do this before taking the derivative, because if we had plugged in before taking the derivative, well, now p and q have become constants, and if we tried to take the derivative now, we would just get zeros. So it's important not to plug stuff in like this until after you take the derivative, because if you plug in before you take the derivative, you're just going to be taking the derivative of a constant, and you're going to get 0, which is not going to be the correct answer. Okay, so let's work this out. So 200 squared, that's 40,000. And then 480 squared, that works out to be 230,400. Add those together. We're going to get s squared is equal to 270,400. And then we take the square root. When we do that, we get 520. So that's what we plug in for this mysterious s now. So we've got 2 times 200 times negative 100 plus 2 times 480 times negative 160 is equal to 2 times 520 times ds dt. And now all that's left is to do a little bit of algebra. The left-hand side is going to work out to be negative 193,600. On the right-hand side, 2 times 520 is 1040 times ds dt. Then we divide both sides by 1040. So we get negative 193,600 divided by 1040. And that's going to be miles per hour. And again, we can throw that in our calculator. We can reduce that fraction, but that's going to be our exact answer. So again, follow the steps here, see how we pulled the information out of the problem. We figured out what the quantities were. We found a relationship between the quantities. We took the derivative. We had some missing information, but we went back to the original relationship and figured that out. And then we plugged everything in and solved. Okay, so one last thing I want to tell you here, and that is some of the formulas that you might find useful. So again, in some of the problems that you'll see, I'll give you an equation that relates the things together, but in some of them, then you'll have to figure that out yourself. So sometimes we'll need area formulas, so area of a rectangle, area of a square, area of a triangle, area of a circle. You may already know many of those. Some of those you need to review. Again, use this slide. Here, these should be volumes, so that should be a V. This should also be a V, sorry for the typo there. So volumes, we've got volume over rectangular solid, length times width times height. Sphere, 4/3 pi r cubed, that's another good one to know. We saw the Pythagorean theorem come up in the example that we just did. You might also use SOHCAHTOA. So if you have a triangle and some of the angles are involved, in the previous example, we didn't care about any of the angles in that problem, so there wasn't any reason to use trigonometry. But in some problems, you might need to know about the angles, so those might be useful. And then the distance formula. So these are all things that may come up and things that you might be responsible for on an exam. So just things to keep in mind. So I hope this was a useful video. Again, watch it a couple times, try some practice problems. The number one thing that you need to do for this related rate stuff is practice, practice, practice. So I've got lots of practice problems that I'm going to be sending you. So if you've got those handy, start to work those out. If you get stuck, pull up the video, try to find one of the problems that we just did here that looks maybe a little bit similar. Try to model your solution after that and see what you can do. Look at the solutions to the sample problems that I'll also be sending out. But again, try some on your own, right? So you need to practice problems on your own from start to finish to see if you can do it. And if you can't and you get stuck, reach out, let me know. So good luck, and I'll be back soon with another video.